Hi everyone. This is the sixth time for the integrations of complex variables. Today we are going to talk about various properties of power series in section 71, 72. Integration and differentiation of power series, yeah, which is described in section 71, and uniqueness of series representations, Taylor series or Laurent series, which is described in section 72. We are looking at integration and differentiation. Okay, before we looking at the main theorem and results, we are going to review some notions. The first is absolutely convergent. In section 61, a series of complex numbers is called converges absolutely if the series of absolute values of those numbers converges. In calculus, we already studied a similar notion with real numbers, but in this case, we consider complex numbers and also series. In this setting, a series is said to be absolutely convergent if it satisfied with this summation absolute value of Gn. Absolute value of Gn is computed by this square root xn square plus yn square of real numbers converges. In the case of complex numbers, in contrast to the real numbers, where we just need to consider two directions, negative and positive directions in the number line. But in the case of complex numbers, we should consider a plane. So there are many directions to converge to something, some complex numbers. So we need to consider to restrict. I mean, what I mean here, distance from the limit, between the limit and converging point, complex numbers. So that is absolute value of here. You can see these circles can be shrink as Gn goes to some point. In the corollary 2, absolute convergence of a series of complex numbers implies the convergence of series. That is, if a given series of complex numbers converges absolutely, then it also converges in a normal sense. In section 61, we consider any series of complex numbers for the notion of absolute convergence. So we can apply it to the power series of complex numbers, so which means if a power series of absolute value of complex numbers converges, then we say the power series converges absolutely. Okay. In section 69, I think last time, we have learned that theorem 1, which says if a power series given by this converges when g is equal to g1, where g1 is not equal to g0, then it is absolutely convergent at each point g in the open disk defined by absolute value of g negative g0 is less than r1, where r1 is equal to g absolute value of g1 negative g0. This theorem says actually opposite direction for the corollary 2, because it says a given power series converges, then it converges absolutely. Okay, you can see the difference between the two theorems here and here. In the last time, we have studied some notions, terms, and what uniform convergence. Also, suppose that a power series has a circle of convergence, which means absolute value of g negative g0 is equal to large R. The sum of power series Sn is defined by this. Summation n is equal to 0 to infinity an times g negative g0 to the n. We also defined partial sum of the power series S of n is defined by this. Finite sum of terms from n is 0 to n large n negative 1. We also defined the remainder function rho n of g, which is difference s of g negative s sub n of g, which is computed by this summation. It starts from large n, which is a variable, and to the infinity for this term an times g negative g0 to the n. Since the power series converges for any fixed value of g, when the absolute value of g negative g0 is less than larger, we know that the remainder rho n of g approaches 0 for any such g as n tends to infinity, because this term comes to closely Sn of g as n goes to infinity. Okay, so the remainder rho n of G would be 0. According to definition 2 in section 60 of the limit of a sequence, we have learned for the notion of convergence as a epsilon statement here. You can see equivalently we can say corresponding to each positive number epsilon, there is a positive integer n epsilon which is satisfied with this. Whenever large n is greater than n epsilon, we have this absolute value of rho sub n of G is less than epsilon. Every terms whose index is greater than n epsilon, its absolute value is less than epsilon. When the choice of n epsilon here depends only on the value of epsilon, for the given initially here. So which is independent of the point G. There is no relation with them. Okay, in this case, we say the convergence is uniform in that region.